peek at our homework for the weekend, worksheet number 6 on Coulombs Law. Specifically, we're going to look at 4 questions, 3, 4, 6, and 7, starting with question number 3. It says an electric force of 7.19 times 10 to the negative 8 newtons acts between two charges, both with the same magnitude, 2.00 times 10 to the negative 2. What's the distance between the two charges? So we're looking for the value of R. The equation that we use here is, of course, Coulomb's law, KQ1, Q2 over R squared. By the way, that looks a lot like another law that we've seen before in Physics 20. Do you guys remember what that other law was? We talked about this last week. What is it? Yeah, it's Newton's law of universal gravitation. They're both similar in the sense that we call them both inverse square laws because the force is inversely related to the square of the distance. That's what they have in common with each other. What makes them different? What makes Newton's law of universal gravitation with Coulomb's law different with Coulomb's law? The magnitude, yeah. Which one's going to be a bigger force normally? The electric force or Coulomb's law force? And what's the other difference between them besides magnitude? Your hint is they're both vectors, right? So what's different about them? Magnitude and, Nick? Direction, right? The gravitational force is always an attractive force, whereas the electric force can be an attractive force or a repulsive force. All right, this is Coulomb's law. We're going to rearrange this equation to solve for R. If it was Newton's law of universal gravitation, we would rearrange it to solve for R in exactly the same way. Here's what I'm going to do. I'm going to take the R squared up by multiplying since it's on the bottom. The first thing I got to do is get it on the top. So it becomes F times R squared equals KQ1, Q2, right? I multiplied both sides by R squared. It canceled out on the right-hand side, and it appeared on the top on the left-hand side. Now I've got to take down the F by dividing. So it becomes R squared is equal to KQ1, Q2 over F. So what I've done here is divided both sides by F. It canceled out on the left side, and it appears on the bottom on the right-hand side. Now, finally, what do I got to do now to find R? Once I get to this point, what is it, Logan? Good, square root it. So R becomes the square root of K, Q1, Q2 over F, right? I'm square rooting the R squared as well, but square root of R squared is R. So here's what I've got. R is equal to the square root of K, which is 8.99, times Q1, which is well, they're both the same, 2 times 10 to the negative 10. I'm just going to square those. Divide it by F, which is 7.19 times 10 to the negative 8. Now let's do the math here on the calculator. We're going to say, let's get what's inside the square root sign first. 8.99 times 10 to the 9 times, I'm going to use some brackets here, 2 times 10 to the negative 10. Squared, or I could have just multiplied it by 2 times 10 to the negative 10 again. Let's divide that by 7.19 times 10 to the negative 8. Got it? Press equals, press enter. This is what I get for what's inside the square root. Then I've got to square root it. Watch very carefully what I'm going to do here, though, okay? Watch what I'm going to do next. I'm going to do something that a lot of you do, but that will get you the wrong answer. Okay? Watch. 8.99, here's what a lot of people do for the times 10 to the thing, right? Times 10 to the 9. How many people do that? How many people do it that way? Okay, that works fine if it's on the top. If it's on the bottom, there's a good chance it's going to lead you to a mistake. Watch this. Okay, this wouldn't give me a wrong answer so far. Times it by 2 times 10 to the negative 10 squared. That's not going to give me a wrong answer yet. Okay, so far that's okay because those numbers are all on the top. But now let's divide that by 7.19 times 10 to the negative 8. Look what happens. I get 5.00 times 10 to the negative 19. Well, it's supposed to be 5.00 times 10 to the negative 3. Okay, what's the problem there? Hamish, what's the problem? Yeah, like, Yeah. I know what you mean, though. Yeah, you didn't quite say it right, but you meant the right thing, I think. In the end here, when I multiply it by 10 to the negative 8 here, because of the way that I've expressed this in the calculator assumes that I'm multiplying these numbers, dividing by 7.19, and then multiplying the whole thing by 10 to the negative 8. In other words, it becomes on the top, right? So you either get these brackets on the bottom or do what I did up here. 7.19 second function, EE, negative 8. That's the way your calculator and the people that designed this calculator intend for you to do times 10 to the whatever, because that puts it with the number. Okay, that puts it with the base. That makes your calculator assume that the 10 to the negative 8 goes with the 7.19, as opposed to what you've done up here, which is assuming making your calculator assume that the 10 to the negative 8 goes with the whole thing. Does that make sense? So I'm suggesting to you that you don't use the times 10 to the hat negative 8, but you rather use the second function EE negative 8, because that'll always work for you, always. The other will sometimes work for you. Okay, this always works for you. All right, so I ended up with what? 0.005001. Okay, and then I got to square root that, of course. I get 0.0707. I'm going to round that to 7.07 times 10 to the negative 2, although it didn't say it had to be in scientific notation, so that would be fine to put it in standard. If this was B times 10 to the negative W, then the answer would be 7.07. If this was A decimal BC times 10 to the negative D, the answer would be 7072. All right? How many people had an issue with rearranging that one? Okay. I suspect that some of you got this wrong because you punched into your calculator times 10 to the whatever as opposed to the EE button. Okay, so be careful with that. Don't make that mistake again. 4. Two identical charges are separated by a distance of 1 meter. A repulsive force of 3.60 newtons acts between the charges. What's the magnitude of each of these charges? They're both the same. They're both the same charges. So we know that they both have the same value, Q1 equals Q2. If I want to find the magnitude of those charges, let's plug it into my Coulombs Law equation, Q1, Q2 over R squared. But you know what? If they both have the same value, then let's just call them the same thing. K times Q over R squared. See what I've done there? Is that okay? Like whatever Q is, it's the same, so we can call them the same thing. Well, let's simplify this a little bit. Let's call it KQ squared over R squared. Because as long as Q is the same as Q, then we can multiply them together and get Q squared. Now I'm going to rearrange this to solve for Q. The R squared goes up by multiplying. The K goes down by dividing. And now I'm going to square root both sides. And I end up getting square root of FR squared over K. Same deal here, right? You're dividing by 8.99 times 10 to the 9. Don't say 8.99 times 10 to the hat 9. Say 8.99 second function EE 9, and it'll work out for you. Okay, Q works out to be 2.00 times 10 to the negative 5. And it's going to be the same for both charges here because they're identical charges. Number 6, calculate the initial acceleration of the alpha particle of an alpha particle. If the alpha particle is this far away from an electron and it is free to move, what's the magnitude of the acceleration of the electron if it's free to move? By saying that they're free to move, it just means that, like, look, if they're fixed in one place, they're being held in one place, they experience a force, but they couldn't accelerate, right? If they're free to move, then they accelerate. We got to find their acceleration. Remember that when you're looking for an acceleration in physics 30, 99% of the time, what you're going to do is get a force. Like an electric force in this case, sometimes it could be a magnetic force or some other force. Get a force, and then use F is equal to m times a. Shibo? Yeah. So here, let's calculate the force first. I'm going to say K Q1 Q2 over R squared. That's 8.99 times 10 to the 9 times Q1, which is, they tell me it's 3.2 times 10 to the minus 19 coulombs, although we could find that on our data sheet. On our data sheet, it would say plus 2E, 2 times the elementary charge, which is 3.2. The electron is 1.6. It's actually negative 1.6, but remember, we always drop the sign of the charge in this equation. The distance is 2.00 times 10 to the negative 25. I'm going to do this on the calculator again, and I'm going to ask you to take out your calculator and enter the same keystrokes. Okay? We want to avoid that times 10 to the whatever thing. Here's what you want to do. 8.99, second function, EE, 9. Okay, now, even though that's a numerator, it's on the top, so it doesn't really matter. You'd get away with using the other way of entering it, but we want to get in the habit of using the EE. Yeah, bracket, but I think this is a better way. Times 3.2 EE negative 19 times 1.6 second function EE negative 19. What I usually like to do at this point is press enter. Get the number on the bottom, or sorry, on the top. Then let's divide it by, let's use some brackets here, 2 EE neg 23, and then let's square that. Now, because I've used brackets here, I would have gotten away with the other notation as well in this case because of the brackets. But again, habit, because still probably, you know, you do it the other way, 80% of the time you're probably going to get it right because of brackets and numerators and so on, but 80% is not good enough. Okay, we want 100%. That works out to be 1.15072 times 10 to the negative 10 to the positive 22 newtons. Wait a second. I have 10 to the 22 on my sheet here. Sorry, what is it? Oh, yeah. So my denominator, I typed in wrong. It should be 2 times 10 to the negative 25, not 10 to the negative 23. So this is what it should be, 1.5072 times 10 to the 22 newtons. Now, if you want to find the acceleration of the electron, or the alpha particle, I should say, let's use the mass of the alpha particle and the force. And that mass, by the way, where are you going to find that mass? I don't know what the mass of an alpha particle is. I do because I've used it so many times. But if I was in your spot, I wouldn't know what it was. So where are you going to find it? Yeah, it's on your data sheet. Divide those two numbers and we get 1.73 times 10 to the 48. That's a big acceleration, a huge acceleration, but it is what it is. Now you want to find the acceleration of the electron. What would you expect the acceleration of the electron to be, bigger or smaller? It's a smaller mass, so it's going to give you a bigger acceleration. Smaller mass, bigger acceleration. Works out to be 1.26 times 10 to the 52 meters per second squared. Number 7 is the last one we want to go over here today. It says a charge of 2 coulombs is touched with the second charge, then with a neutral, and then we want to find a force between them. This is one of those two-steppers. We did an example just like this. Charge 1, charge 2, charge 3. Let's find out what they become after they touch each other, and then let's figure out what the force is. We start off with 2 coulombs, 6 coulombs, and 0. And it says that 1 touches 2. 2 plus 6 divided by 2 is 4 and 4. Then it says the first one touches the second one, then the first one touches the third one. So now it's 4 and 0 touch each other. That's going to become 2 and 2. And the second one is still 4. So you want to find the force now? We're going to say K Q1 Q2 over R squared. 8.99 times 10 to the 9 times Q1, which is 2. Now it is. What? I guess it's the way it started as well, but it's 2 because of all the changes, not because that's what it originally was. The second one is 4 divided by 5 times 10 to the negative 2, and we got to square that. Remember, on your calculator, that's 5. Second function, EE neg 2. That's the best way to do it. Can we do the math there? It's going to give us 2.88 times 10 to the 13. We're getting really big forces for some of these questions. Can anybody suggest to me why those forces are so big? Yeah.
Because because it's on the smallest level, there's very, very little mass.
Oh, okay, but even without mass, the force, like mass doesn't appear in that equation for force, right? So even if the mass is really small, and it is, that's not going to affect the value of the force. It would affect the value of the acceleration. The force is so big because the charges are so big. Remember we said that Coulomb is a big unit of charge? But yet we're dealing with coulombs here. We're dealing with really, really, really big charges. So we're going to be dealing with really, really big forces as well. And then because of that and the small mass, we're going to be dealing with gigantic accelerations. Right, Hannah? We're good there? All right, I want to take a look at one example question. That's what we're going to wrap it up here today with that one example question. It's the first one, example number 1 on the handout that I gave you a few minutes ago. Looks like this. It says find the net force on sphere B due to spheres A and C. So we got 3 charges. We want to find an electric force. What are we going to do? F is equal to K Q1 Q2 Q3 over R squared. Does that work? No, it doesn't. Good, Chase. It doesn't work because it messes up all the units, right? Like if I had KQ1, Q2 over R squared giving me newtons, then I can't just arbitrarily add a third charge in there and still expect to get newtons. So I can't change the equation. So what am I going to do? Add them all up and divide by 3 to get the charges? Well, no, they're not touching each other. They're not touching each other, right? If they were touching each other, then yeah, I would do that, but they're not. So what are you going to do? Chase? Yeah, separate equations and then combine them. Before I do the separate equations, though, what I want to do is draw a free body diagram. You guys remember what a free body diagram is? Shows the direction of what? Yeah, it shows all the forces acting on an object. There are 2 forces acting on object B. Here's what you got to do, guys. When you're looking at object B, the force on object B caused by A, what I want you to do first is pretend that object C doesn't exist. Pretend it's not there. Now, are these guys going to attract each other or repel each other? They repel, and how do you know that? Because they're both positive. The like charges repel. Now that means that B will be pushed this way because of A. I'm going to call that FAB, the force of A on B. Now, A is pushed this way with an equal and opposite force, right? FBA. But guess what? I don't really care about that one. Even though it's there, and even though I know that it's equal and opposite to FAB, I don't really care about it because I'm trying to find the force on B. Make sense? All right. Now what I got to do is pretend that A doesn't exist. Now I've got to look at the force of C on B. Are C and B going to attract each other or repel? They're going to attract because they're unlike charges, opposite charges. So that means that B will be pulled towards C, right? If this is C and this is B, look at my hands here. B and C are pulled towards each other. So B gets pulled to the right as a result of C. FCB is to the right. Now, charge C gets pulled to the left, right? Towards charge B. But I don't really care about that one right now because I'm not trying to find the force on charge C. There's my two forces. Now, we're going to go exactly with what Chase suggested a few minutes ago, calculate both of those forces. Now let's add them up, combine them. We're going to say the magnitude of FAB is K QA QB over R squared. QA is 2 times 10 to the negative 6. That's what a microcoulomb is, right? 10 to the negative 6 times 3 times 10 to the negative 6. Divided by the distance, 2 squared. Let's figure out what that value is. Let's say 8.99 second function EE 9 times 2 times 10 to the negative 6 times 3 times 10 to the negative 6. And now let's divide that by 2 squared. 0.013485. And now let's get FCB. You see is 1 microcoulomb. Notice it's -1, but remember we always drop the sign of the charge here, plugging it into this equation. Let's figure out what this one is now. 8.99 times 10 to the 9 times 1 times 10 to the negative 6 times 3 times 10 to the negative 6. Divide that by 1.5 squared. 0.011987. Now, Chase, when I combine these, what am I going to do with them? Add them or subtract them? Yeah, really, I'm always going to add them, but if one of them was right, one of them was left, I'd add a negative value, which is the same thing as subtract. But since these are both to the right, I'm going to just straight off add them, right? The net force is equal to 0.013485 plus 0.011987. Again, if one of them is to the left, make it a negative value. This gives me 0.0255, which is 2.55 times 10 to the negative 2, which expressed as B times 10 to the negative W would be 2.55. Expressed as A decimal BC times 10 to the negative D, we get 2.552. Okay? So, you got to draw the free body diagram. Please, 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 please don't skip that step. Got to draw the free body diagram. And when you do that, look at 2 at a time. Pretend the third one doesn't exist. Pretend the first one doesn't exist. Look at 2 at a time. Even if you're looking for the force on A, we would find the force of B on A, pretending C doesn't exist, and then the force of C on A, pretending B doesn't exist. Always do one at a time, pretending the other one doesn't exist. All right? Here's your homework for tonight. In addition to practice question set number 9, because we're going to have a quiz on that on Wednesday, that's just the straight off Coulombs Law stuff, right? Not the 3 charges. In addition to those, I want you to do question number 1, just question number 1 on your Coulombs Law number 2, worksheet number 7. Okay, just question number 1. Now, there's an A, B, and a C to it, so there's a little bit of work to it, but it's not an onerous amount. Remember what I've always said, though, guys, right? How long should homework take you max? Half an hour, right? If it's taking you longer than that, then you're having some trouble. Come and see me.